The next module which we will be focusing now is about the gradient descent. So frequently when doing data science, we'll be trying to find the best model for certain solution of certain situation. And usually best will something which will be related to which minimizes the error of the model or maximizes the likelihood of the data. So basically, in other words, it will represent the solution to some sort of optimization problems. This means that we'll need to solve a number of optimization problems, and in particular, we'll need to solve them from the scratch. Our approach will be a technique called gradient descent, which lends itself pretty well in such a condition that you might not find it super exciting at the initial stage, but it gives a path for particular solution. Say for the given graph which is given over here. This particular path which is referring the x, y and z axis is actually the gradient descent. So we'll frequently need to maximize or minimize such functions for the normal functions in the vector, but in gradient descent it is just like you have to keep it like a calculus. So this is a partial derivative which gives the input direction in which the function most likely increases. So if you don't remember the calculus, take my word for it and look it up on the internet. You'll get the same issue which is needed. So accordingly, one approach to maximizing a function is to pick up a random element, say from a particular point, and compute the gradient, take a small step in the direction of the gradient and repeat with a new starting point. So similarly, you can try this with the minimize function by taking small steps in the opposite direction. So if a function has a unique global minimum value, the procedure is likely to be found out. So let's go to the code base where I'll show you the basic analysis of estimating a gradient through a simple function. Say for the function, say if is a function of a variable and its derivative at point x measures how f of x changes. When we make a particular change to x, then it is defined as a limit of the difference quotients. So that is done as df difference underscore quotient with the value as f comma x comma h, and this value will be represented over here as return f of x plus h minus f of x with the value divided by h. Now here you can see it is nothing but an f function. So it takes f as a function of one variable, its derivative at a point x, and how it measures the particular. So this is a simple example of a gradient quotient. So this can be even plotted to get the squares and the derivative if needed. So the next chapter is all about understanding the actual derivatives and the estimates and plotting up for the same. So this gives you a better analysis of a gradient quotient. So let's get started with the next chapter.